Good evening, everyone. My name is Andrew Fracknoy. I'm the Emeritus Professor of Astronomy at Foothill College, and it's a great pleasure for me to welcome all of you to this first talk in the 22nd year of the Silicon Valley Astronomy Lectures. For the last 20 plus years, we've brought you talks from noted astronomers explaining the most recent developments in astronomy. And we welcome people from all around the world who watch us on YouTube. I should say that this program is co-sponsored by 4 different organizations: the Foothill College Science, Technology, Engineering, and Math Division, the SETI, or Search for Extraterrestrial Intelligence Institute in Mountain View, the Venerable Astronomical Society of the Pacific, and the University of California observatories, which includes the Lick Observatory, the first permanently inhabited mountaintop observatory in the world. We're delighted tonight to welcome a very special speaker, Dr. Emily Levesque of the University of Washington. Dr. Levesque is an astronomy professor at the university and is the author of a critically acclaimed popular science book entitled The Last Stargazers, published in 2020 by Sourcebooks. Dr. Levesque's work explores how the most massive stars in the universe evolve and die. As part of her work, she's observed for upwards of 50 nights on many of our planet's largest telescopes, and flown over the Antarctic stratosphere in an experimental aircraft as part of her research. Her academic awards include the 2014 Annie Jump Cannon Award, a 2017 Alfred P. Sloan Fellowship, and the 2020 Newton Lacey Pierce Prize given by the American Astronomical Society, our research organization for astronomers in the country. As I say, Dr. Levesque has written a book called The Last Stargazers. It is full of great anecdotes from her own life and development as an astronomer and from astronomy as it happens in the real world. And that's, in fact, what she's going to tell us about. She's going to talk about astronomy behind the scenes, The Last Stargazers. Ladies and gentlemen, it's my great pleasure to present Dr. Emily Levesque.
Hello, everyone, and thank you so much for inviting me to speak as part of this lecture series. I'm very excited to talk to you tonight about The Last Stargazers. So The Last Stargazers is the book that I wrote about a sort of behind the scenes peek at what it's like to be a professional astronomer. And as part of writing this book, I got the chance to, for the first time, learn about the publishing industry. As somebody who was trained as an astronomer, I didn't really know a whole lot about how one wrote and then sold books. And it was a wonderful world of book lovers to get introduced to. And while I was sadly mostly marketing my book as the pandemic was beginning, I did get the chance to go to one wonderful book event, the Public Library Association conference in February of 2020. And at that conference, I got to talk to a lot of other authors. I got to sit on panels. And at these panels, we talked about the first lines of books and the amazing tone that gets set by the famous opening lines we all remember from our favorite books, Call Me Ishmael, It Was a Dark and Stormy Night. People put so much weight into first lines and look at how they set the tone for whatever world you're introducing people to. So it got me thinking, okay, well, what's the first line of my book? I'm introducing people to what it's like to study the cosmos and dedicate your life to exploring the universe. What's the first line that welcomes people into this world? And I realized the first line of my book is, have you tried turning it off and on again? So I start my book the way every phone call with your internet provider starts. But I have a good reason. This is actually the most petrifying thing that's ever been said to me at a telescope. I was asked this while sitting here. I was sitting at the Subaru telescope at Mauna Kea Observatory in Hawaii. I was a graduate student at the time, and I had been granted a very hard to get night on this telescope to take observations for my thesis. I was studying the galaxies that hosted dying stars billions of light years away that were blasting gamma rays into the universe to try and understand how these stars worked. And this was one of the only telescopes in the world capable of doing this. I'd been having a good night. I'd applied for this time. I'd been granted hours to do this research. I'd been going through my research plan and everything was going great. And then halfway through the night, one of the computers in the telescope's control room made this awful sort of blunk sound. And I looked over at it. And then I looked at the only other person on the mountain with me, who was the telescope operator. She was looking at the computer too, which was my first clue that something was wrong. And then she tried to reassure me about the sound by saying, "Oh no, don't worry, it's okay. I think the mirror is still on the telescope." And this was not the reassuring comment I had hoped for, because I didn't know that there was an option for mirrors to not be on telescopes. She went on to explain to me what had happened. This telescope, like many of the others that are used professionally today, consisted of two main mirrors. The primary mirror, or the biggest mirror, the mirror responsible for capturing the starlight that I was observing, was huge. It's 8.2 meters from end to end, so over 27 feet. For scale, that's me standing beneath another mirror that's about the same size at a telescope in Chile. So this mirror, when the telescope was operating properly, as is currently being demonstrated by a picture of the Palomar telescope in California, would sit sort of near the bottom of the observatory dome. And then high above that primary mirror is this telescope's secondary mirror. It's suspended above it, responsible for re-reflecting the light captured by the primary and then directing that light into a camera or a spectrograph or whatever scientific instrument I was using. The bloop sound had been telling us that the mechanized supports holding up that secondary mirror had failed. And the implication was that the telescope was probably still fine because it was pointed mostly straight up. But if we moved the telescope too much, if we tipped it to one side or the other, nothing was supporting that that secondary mirror anymore. And we risked it sliding off the telescope and plummeting about 70 feet to the concrete floor of the observatory. And that was if we were lucky. If we were unlucky, it would hit that enormous primary mirror on the way down. So we put in a call to the day crew of the observatory, sort of the engineers that worked on the telescope during the day, to ask them what this alarm meant and what we should do. And a very cheerful crew member said, "Oh, it's probably not a problem. It's probably just a false alarm. We saw that during the day. It's probably the same issue. There was far too much probably happening in this conversation. You can probably fix it by just turning the telescope off and on again." So he was proposing power cycling a building-sized telescope like it was a modem, but it seemed a little impolite to point out, this isn't the troubleshooting model that I'm really on board with. So the telescope operator then turned to me and said, "What do you want to do?" I was 24. I was a grad student. I really wanted to keep observing because this was my only night on this telescope. If I just gave up when the telescope could be fixed by a power cycle, I would be losing precious telescope time. But if I kept going and accidentally did drop the secondary mirror off the telescope, I knew I would be known forever as the grad student that killed Subaru. And sitting at the telescope, all of these stories were spinning through my mind of telescopes that had had something go horribly wrong. The one that kept coming back again and again was this one, which is the Green Bank Radio Telescope in West Virginia. This was a beautiful, enormous radio telescope, 300 feet from end to end, and the most powerful radio telescope of its day, until one evening, it suddenly went from this to this. It suffered a catastrophic collapse in the middle of the night, in the middle of actually actively observing. I knew this story. Sitting at Subaru, I was convinced that this had happened because somebody had tried turning it off and on again. So I was stuck at this telescope alone on a mountain trying to decide what to do. And this is the story that I actually used to open my book. because it gives you a sense of what astronomy and working at these telescopes can sometimes be like. It sounds like it could be a very peaceful job, just sitting and watching the stars, waiting for something interesting to happen and using these beautiful machines. But it can be underlain with a lot of tension, knowing that you only have so much access to telescopes like this and knowing just how many things there are that can possibly go wrong. And this glimpse of how we actually do the science is what I wanted to come across in The Last Stargazers. It's really not hard to sell people on space and the beauty of space. Everybody loves pictures of space. We've seen all these amazing photos from the Hubble Space Telescope or our other world-class telescopes, including facilities like Subaru. And we love just admiring the galaxies, the stars, the really colorful gas. But what not nearly as many people know about is where these pictures actually come from. If you ask people to picture an astronomer and picture a professional working astronomer, you tend to get back pictures like this. This is what happens if you search astronomer stock photos on the internet. So you tend to see men. They tend to be wearing lab coats for unclear reasons, because we don't usually need a lab coat to observe. They tend to have beards, apparently. And they're usually standing next to a cute little telescope on a tripod and looking through it with their eye. And it's a fair picture because this is the experience most people have of stargazing. This is what we do in our backyards or when we go to an astronomy open house. So we just imagine this with a lab coat sort of done professionally. In reality, the true job of being an astronomer is very different, but it's not one that a lot of people tend to run into. There's 7.5 billion people on the planet, and only about 50,000 of us are professional astronomers. So it's completely fair that most people won't be sure of what we do all day. Despite that, you can still find a lot of people interested in astronomy and curious about our jobs. I was absolutely one of those people, even as a very little kid. So this is me at age 6, very proudly sporting my Hubble Space Telescope t-shirt because Hubble had launched that year. At that point, I already knew that space was cool. I had a children's book about black holes, and I knew that studying stars and doing science forever sounded like a really great job. But I didn't know any professional astronomers. I didn't know any professional scientists. We had a little telescope that we got to take out in our backyard. This is me and my dad using our beloved Celestron. So I did sort of picture just that in sort of grand scale. My best glimpse of what professional scientists did actually came from the movies that I saw growing up. So based on the movies that I watched with scientists in them, and especially with women scientists in them, I, from Twister and Jurassic Park, learned that if you're a scientist, your research chases you a lot of the time. And even from Contact, I got the sense that while it was a wonderful story, you probably didn't discover aliens every day. So this was as much as I knew about professional science until I was in college. After my sophomore year of college, I got the chance to attend my first summer research program. I traveled out to Arizona and worked with Dr. Phil Massey, who's still a colleague of mine today. And we started our work together by traveling to Kitt Peak National Observatory. We had plans to observe dying stars for 5 nights to try and figure out the physics of those stars and how they worked. So this was my first time at a professional observatory. We drove up the mountain, we dropped our stuff off in the dormitory, and we showed up in time to have dinner as the sun was going down. So we walked into the cafeteria. There were a bunch of other astronomers eating. We sat down at a table. Everybody seemed to know Phil. And Phil introduced me saying, "Hi, this is Emily. She's a student working with me, and this is her very first night at a professional observatory." And the whole table got excited and said, "Oh, welcome, you're going to love it. Remember to order your night lunch." This is the extra meal that astronomers have at like 2 a.m. to get fed halfway through a night shift. "Remember to order your night lunch, but don't eat it too early. You'll get hungry at 11, but try to hold out." And then someone else said, "Remember to drink coffee. It'll help you stay awake, but stop drinking coffee at about 3 a.m. Otherwise, you'll be too keyed up to go to sleep." And then a different person chimed in saying, "Well, keep an eye on the floor around your control area because we have scorpions on this mountain." And there was actually a woman who had a scorpion crawl up the inside of her pant leg and sting her while she was observing. And then someone else said, "Oh, that's nothing. I know a guy that had a raccoon crawl into his lap while he was observing back when you worked in the dark dome." And then someone else said, "Well, I know a guy who was observing when the side of the telescope caught fire." And someone else said, "Well, there's a story about a telescope that got shot." And these stories started pinging back and forth. And I was sitting there with my fork halfway to my mouth, just sort of gaping at everybody. And I couldn't decide whether I wanted to just stay there all night and hear the stories they were telling, or run off to the telescope and see about making some stories of my own. And years later, it occurred to me what this storytelling session had really done, because it was sort of how people were welcoming me to the field and saying, this is a kind of funky job. It's not quite like anything you've done before. Here's a glimpse of what it's going to be like. Here's what some of these shared experiences are like. Here's some of the stories that we pass around the field to tell people what our jobs are. And years later, the memory of that storytelling welcome is what inspired me to write The Last Stargazers. So this book gives people this behind the scenes glimpse at life as a professional astronomer. There are wonderful books out there about the science of astronomy, answering a lot of the questions that we have about the universe. But I wanted to combine the science that motivates what we do and the science of how telescopes work with these human stories to try and sort of put a personal face on a field that can often seem really far-flung and esoteric. The book has gotten nominated for and become a finalist for a bunch of science writing awards. If you're curious, you can learn more about it at thelaststargazers.com, or you can follow me on Twitter at Empsk, and you can follow the hashtag #TheLastStargazers to see the latest news about the book. When I first started writing the book, I knew that I wanted to visit a bunch of observatories, explore a lot of the different ways that we can do astronomy. And I got the chance to have some really fantastic adventures as part of writing this book. I got to visit observatories in Hawaii, in Chile, in California. I got to visit clean rooms and laboratory research areas that were just fascinating. I got to travel on an experimental aircraft, which I'll explain in a little bit. But I think my favorite part of doing research for the book is actually that picture on the lower right. That's a picture of my trusty voice recorder, which I used to interview more than 100 of my colleagues for this book. I wanted to gather as many astronomy stories as I could from other astronomers and have them tell me about their most memorable nights of observing, what they loved the most about observing, what drove them nuts about observing, and how they had experienced sort of their introduction to the field over the years. For the most part, I just let people talk. People would start telling me their stories. I would sort of guide them along to the kind of tales that I want heard, and I would let them drive the interview. But there were a few questions that I asked everybody because I wanted to use these questions to help stitch together the overall narrative arc of the book. And these are the 3 questions that I'll be answering during the rest of this talk. The first question that I really liked asking people was, what is your most memorable secondhand or third-hand or 10th-hand observing story? And I was specifically here looking for the stories that someone had heard from somebody else's advisors, colleagues, other friend at a conference that one time that was this tall tale that couldn't possibly be true. They would half remember the details. They knew they weren't quite telling me the whole story, but it had stuck in their mind so hard that they just had to share it. The idea was that I would get these stories that had entered the sort of legendarium of the field. And my hope was that I could find these stories, track them back to their original sources, and then use them to talk about these sorts of tales that really stick in the minds of astronomers. There were a couple answers to this that I got again and again. I think the most common answer that I got points to one of the more surprising stories in our field, which is, do you have the one about the telescope that got shot? I can't tell you how many people asked me this and then proceeded to tell me some wildly inaccurate version of the story. So the telescope that got shot is a true story, and it refers to this telescope at McDonald Observatory in Texas. It's the McDonald 107-inch telescope. Now, I mentioned the size of the Subaru primary mirror before. 107 inches here refers to the size of the telescope's primary mirror. It's pretty much the most important thing about a telescope is how big its primary is, how much light it can gather, and how dim an object it can observe. When the 107-inch was built, it was actually the 3rd largest telescope in the world. It was an absolute jewel of this observatory. And this telescope was unfortunately the victim of a shooting one evening. People told me so many different versions of who the shooter was in this story, and they'd imagined all sorts of very dramatic tales. There were tales of a graduate student angry at their advisor. There was a spurned lover storyline at one point, or deep scientific rivalries. In reality, the shooter in this story was an unfortunately distressed and disturbed member of the observatory staff. And one evening, this staff member, under the influence, became hell-bent on destroying this telescope. He entered the telescope and the control room of the telescope and demanded that the telescope operator lower the telescope so that it would be pointed pretty much parallel to the ground, so you could look right down it to that enormous primary mirror. The telescope operator saw the pistol in his hand and did as he was asked. And the shooter then emptied the pistol, firing 7 shots into the primary mirror. Now, it sounds disastrous until you think about how primary mirrors are made. These mirrors are enormous. They're big, heavy chunks of glass that then get covered with a sheen of reflective metal so that they can act as a very high quality mirror. If you think about a Pyrex dish in your kitchen, and then imagine a dish like that, but 1.5 feet thick. That's what one of these primary mirrors was like. So when 7 bullets were fired into that primary mirror, they did not shatter the mirror as you might imagine. They sort of went thunk and landed in the glass like darts in a dartboard. The gunman was disappointed with this result. You can see exactly how much damage was done to this mirror. Decided to start trying to go after the mirror with a hammer instead. And at this point, he was fortunately subdued and nobody was harmed. And the damage to the telescope was left as what you see on the screen. So despite this, this was a pretty dramatic event to happen in this very quiet corner of Texas. And word got out that the telescope had been utterly destroyed by this shooting. And in reality, the staff looked in at it and said, oh, those bullet holes aren't too bad. We can probably dig out the bullets. We'll paint the little area black so that we don't see reflections bouncing around the mirror. And really, it's just gone from a 107-inch telescope to a 106-inch. We've lost a little of light collecting area, but the telescope will be fine. This was something that everyone at the observatory knew, but by this point, the story had made the national news. Walter Cronkite actually presented this story before then showing a picture of the wrong telescope depicted upside down. So this misconception that the beautiful new telescope at McDonald had been destroyed got out through the entire astronomy community. The observatory director at the time, Harlan Smith, decided to put out a circular, so sort of a brief statement explaining what had happened at the telescope. Usually when astronomers put out circulars, they're saying things like, hey, there's a weird variable star we found in a nearby galaxy. Someone should check that out. Or a star flared nearby and we got this great data. So in the midst of all of these circulars, one was published reading, yes, this happened, but don't worry. The harm suffered from the bullets was extraordinarily small, which has to be one of the more unusual statements ever put into an astronomy circular. So it's a sort of wacky story about something very surprising that happened at a telescope. But one thing I find interesting about this story is you have to understand a lot about astronomy to really understand the story itself. You have to know why we call this telescope the 107-inch, why the size of that primary mirror is so important, and why it's such a big deal that that mirror might be destroyed. You have to understand what a telescope operator does. This demand that the telescope operator lower the telescope might seem a little odd if you imagine telescopes just being operated by astronomers. In truth, these operators take care of running these big, complicated machines while astronomers work alongside them, kind of directing science. You need to know that it's this big, thick mirror. You need to know why the bullets didn't shatter the glass. And it's worth understanding why this is such a big deal. There really aren't that many professional grade telescopes in the world. So losing even one telescope, particularly at the time, one of the biggest telescopes operating, would have been a major blow to the field and would be a real scientific loss. So all of that context is needed to understand even a one-off story about something extraordinary that happened at an observatory. So do you have the one about the telescope that got shot? Overwhelmingly, the answer that most people gave me. A very close second was this one. People would say something like, there were these weird bursts of radio emission. They were coming from space, except they weren't. They were actually coming from something funny on the ground, and astronomers were confused by them for a while. They would sort of half remember the story of radio bursts that looked like one thing and turned out to be something else. And the true story of this happened at Parkes Observatory in Australia. So this is Parkes Observatory's big, beautiful radio telescope, kind of similar to the one I showed you in West Virginia before. It's an enormous antenna specifically designed to reflect and collect radio light that has made some amazing discoveries over the decades. So back in 2007, Parkes Observatory detected this weird brief burst of radio emission. They didn't know what it was. They'd never detected anything like it before. It caught them by surprise at the time. Years later, an astronomer named Emily Petroff showed up at Parkes Observatory as a graduate student, and she was interested in studying weird radio bursts like this. And she posed this as an idea to the folks at the observatory. And the response was, oh no, don't bother. We actually detect things like this all the time. They're probably not real. They're probably not coming from space. We suspect they're just some weird radio interference on the ground. It's definitely not interesting. Emily wasn't convinced by this and thought that she would try to get to the bottom of what these events were, to see if maybe there were some real flashes of radio light from the other side of the universe coming in amid all these weird signals that we thought were coming from the ground. That explanation was not a strange one, because radio telescopes are very good at detecting passing radio emission from all sorts of things here on the ground. Fluorescent lights emit radio waves, Wi-Fi, the spark plugs in cars, all sorts of things can emit radio interference. And the staff assumed that these strange bursts were something like that. They'd actually given them a name. They'd called them perytons, which is a mythical creature that looks like one thing, but casts the shadow of something else. So something whose identity is fooling you a little bit. Emily wanted to know what was causing the perytons, and she wound up rounding up the whole staff of the observatory to investigate the problem. Their first hint came when they started looking at when the perytons were coming in, and they realized that perytons tended to show up around the lunchtime hour. So the cosmos is a fascinating place, but it does not care what time lunch is in Australia. So this was their first clue that whatever was happening had something to do with lunchtime. They immediately turned their attention to the microwaves that were at the observatory site. The 3 buildings pointed out on this slide are administrative or office buildings in the Parkes complex that would have break rooms and have microwaves in them where somebody might heat up lunch or a snack. So Emily and her team, which eventually included the entire staff of the observatory, everybody on that staff, by the way, wound up on the paper announcing what they had found. They started messing with these microwaves. They read about how the microwaves worked. They read about how microwaves generate the signals that they do. They started running them on high and low power. They ran them for different amounts of time. They very carefully always microwaved a ceramic mug full of water. They were being excellent scientists trying to treat these microwaves very carefully to see if they would produce a peryton, but they didn't. They would microwave things for short amounts of time, long amounts of time on high and low, and the telescope didn't pick anything up. And somebody finally realized that they were behaving like good, responsible scientists, and they weren't acting like hungry people who were waiting for their lunch. Because when you microwave leftovers or popcorn, we all do this. You watch the microwave count down and you think, all right, 3, 2, close enough. And you open the door just before the microwave finishes running. When they did this, when they ran the microwave and opened the door to stop the microwave, they produced a peryton. So then they went back to the data that Parkes had gathered, and they realized they could account for all of these perytons, all of these weird radio bursts that they had detected, except for that burst from 2007. That one was not explainable by this microwave signal. That one was real. We've since discovered heaps of bursts like this. They're now called fast radio bursts, and they're an entire class of strange phenomena that we still don't entirely understand. We think they're coming from the sort of leftover material of dead stars and are still figuring out the physics behind them, but we wouldn't have gotten to explore them at all if we hadn't first eliminated the fault signals from microwaves that were tripping us up. So the people I interviewed loved telling me this story. They got such a kick out of these mistaken signal identity tales because it's a nice contrast, right? Us trying to study things on the other end of the universe and getting tripped up by lunch. And a lot of observatories have versions of these stories. Radio telescopes tend to have the most dramatic or funniest versions of these. And my personal favorite is actually another one that happened at Green Bank Observatory in West Virginia. So the telescope pictured now is the beautiful replacement telescope to the one that I showed collapsing earlier. And they replaced this telescope specifically because this observatory is built in one of the most radio quiet areas on the planet. It's our national radio quiet zone. We make sure that there are no Wi-Fi signals in the area. People who live there don't have Wi-Fi. Their microwaves are kept in special cages. Diesel vehicles are driven near the observatory itself to avoid the little lightning bolt radio signals from spark plugs. They go to enormous effort to keep this area as free of spurious radio signals as they possibly can. But there is only so much that they can control. So this observatory is in the middle, you can see in the picture, of a beautiful state forest area. And there was research being done in this forest at some point on a population of little flying squirrels. So scientists wanted to study these squirrels, study their habitat, study how they behave, study how they migrate and run around. And to keep track of a bunch of tiny squirrels, the best thing to do is to fit them all with little tiny radio collars. So they did this and then unleashed the cutest swarm of radio interference sources that the observatory had ever seen. Apparently, they basically could not observe for a couple of months because they just kept picking up squirrels. You try to study a black hole in the center of another galaxy, nope, squirrels. You try to study radio emission coming from a very strange dying star, nope, squirrels. They wound up closing for a couple of months to do engineering work, and all they could do is wait for the batteries and the little collars to die. So sometimes there's not much we can do. Other times, observatories can be very careful about sort of limiting these noise sources or contaminating light so that they can get pristine data. This sounds like the sort of problem that would really mainly impact radio telescopes, maybe occasionally get a little extra light from optical telescopes, the light we see with our own eyes. But this sort of interference happens everywhere in astronomy. It even comes up when we're not studying light at all. So this observatory is the Laser Interferometer Gravitational Wave Observatory in Hanford, Washington. We have 2 observatories like this in the country. They are some of the most exquisitely engineered scientific instruments on the planet because they can detect gravitational waves, these tiny little density ripples in the fabric of space-time produced when 2 black holes or 2 neutron stars collide. These are some of the most gravitationally violent events in the universe. To detect them, we need to set up this enormous observatory consisting of 2.5 mile long arms that are perfectly straight with huge heavy mirrors suspended at the ends. These observatories are insulated against anything that could possibly shake or jitter those mirrors, so that the only tiny disruption to those mirrors comes from gravitational waves. They will then fire lasers down these long arms to reflect off of those mirrors and detect any tiny perturbation that would come from a gravitational wave. And the worry is that they need to detect those, but not detect earthquakes or trucks driving by or rain hitting the ground or waves on the ocean shelf 200 miles away. These things are amazingly sensitive, and they figured out how to insulate this detector from all of those sources of interference, but not quite everything. This observatory at one point started getting weird little sporadic signals in the detector. And they knew it wasn't seismic activity. They knew it wasn't trucks. They knew it wasn't people's footsteps. They knew it wasn't the wind. They were trying to explain what was going on. And these signals were coming up in the middle of summer. These facilities have to be very cooled. So they have big tanks of liquid nitrogen and big tubes leading into the facility that will wind up getting covered with ice. So you've got this great source of ice in the middle of a hot desert in a hot summer. Somebody took a look at that ice and they discovered the doings of this guy, Thirsty the Raven. They saw ravens hovering at these pipes, sort of pecking at them. And then when they took a close look at the ice, they discovered suspicious peck marks that made very clear that these ravens were poking at the ice, getting a much needed drink on a hot day, and that the pecks of the bird beaks were being picked up by the observatory. They had to test the hypothesis, so they sent a grad student out with a hammer to see if they could reproduce the behavior of the raven. It worked, and they successfully figured out that they weren't detecting gravitational waves, they weren't detecting distant colliding black holes, they were detecting a very thirsty raven. So I'm pretty sure that they figured out a way to clear away the ice or protect the pipes, and this disappeared as a noise source. But even gravitational wave observatories get fooled by these sort of local sources of noise. So another question I asked people as I interviewed them was what they thought would surprise people the most about our jobs as astronomers. What's the biggest disconnect between what people think astronomers do all day and what we actually do all day or all night? One of the big answers had to do with the adventures that we have and what the job is actually like. A lot of people said something like, well, we don't look through eyepieces. We don't stand next to these little telescopes. We actually get some pretty extreme experiences going to the ends of the earth to try and take our data. So we pointed back to these sort of artist depictions of astronomers, the guy in a lab coat standing next to a little tripod telescope, as the stereotype of what we do. In reality, the actual stories are much more exciting. I got to hear about a bunch of these stories over the course of my interviews. I'll admit that there is one guy in this slide who is wearing a lab coat and is standing next to a little telescope. He has an excuse. That is one of the coolest telescopes we've ever built. And if you don't recognize it, I'll tell you about it very soon. One of the great observatories that I got the chance to visit during my research was this one. So this is SOFIA, which stands for the Stratospheric Observatory for Infrared Astronomy. It is a telescope that operates out the open back door of a specially modified Boeing 747 that is able to fly up into the stratosphere higher than where commercial planes fly, and then open that door while in flight. The reason it does this is that the plane gets above all of the water vapor in our atmosphere. It means that that telescope can detect wavelengths of light that would normally get blocked by the water vapor from clouds and never make it to the ground. This is our only way to study that type of light short of going to space. I actually got the chance to visit and fly on SOFIA as part of my academic research. I got to take notes for the book along the way. We wound up flying out of Christchurch, New Zealand, and flying almost into the Antarctic Circle as part of our flight pattern. We flew so far south that we actually saw the Southern Lights from the plane. It's one of the coolest adventures I've ever had in my life relative to my job or really anything at all. And it's one of my favorite stories in the book, sort of getting a visit to what this very strange and unusual aircraft flying telescope observatory is like. So we tend to send telescopes as high as we possibly can to get above as much of our atmosphere as possible. Sometimes it's just a matter of putting telescopes on mountaintops. Sometimes we put telescopes in the back of planes. Sometimes we will even launch telescopes aloft on balloons or suborbital rockets, getting as high as we possibly can to get data. We do send telescopes like Hubble into space, but building a space telescope is a massive endeavor. So the more we can sort of squeak above the atmosphere by mounting a telescope under an experimental balloon, the better we can do and the more science we can get. So I talked to folks that had run balloon missions or rocket missions and about the quirks of doing astronomy with facilities like this. I also got to talk to astronomers who chase eclipses for a living. This is a photograph of a solar eclipse that happened in Svalbard, Norway, back in 2015. The team that took this picture is led by a woman named Shadia Habal, one of the leading solar eclipse researchers on the planet. And she leads teams on expeditions all over the world to chase total solar eclipses. They bring all their equipment with them. They wind up in pretty incredible places out in the middle of nowhere. On this trip to Svalbard, they got warned about polar bears and keeping an eye out for polar bear safety, which is something of an oxymoron. But they get to go to all of these incredible places to get really critical data and observations of the sun during these moments when it's completely blocked by the moon. It gives us a chance to look at the solar corona, the outer edges of the sun's wind, and really learn amazing things about the physics of how our sun works. I also got to talk to people who traveled to places like the South Pole for their research. We have a South Pole telescope that is built quite literally at the South Pole near Amundsen Scott Station in Antarctica. People would winter over and have the experience of spending 6 months at the South Pole working on this telescope and experiencing life in Antarctica as a research scientist. They had incredible stories to share about what it was like to live in an observatory like this for such lengths of time. And then finally, I promised I would explain what this picture is. So that scientist is George Carruthers. He is the inventor of the ultraviolet camera. So a way for us to capture pictures of ultraviolet data, which is much more challenging than getting the sort of data that we see with our eyes. He's standing next to the first telescope that held his invention of the ultraviolet camera, which is a little 4-inch telescope. This telescope was designed to fly on Apollo 16 and is the only telescope we've ever put on the surface of the moon. It was operated by astronauts John Young and Charlie Duke for several days. It took our first ultraviolet pictures of our own planet, of stars in the Milky Way, of our planet's aurora, and it kicked off the same type of astronomy that Hubble is now amazing at. Being in space, it's one of the other telescopes that is capable of taking ultraviolet data. When I wrote the book, I had to sort of keep track of what types of stories I was telling and what scope the book had. And I decided I would mainly focus on telescopes that operated from the ground, rather than telling the stories of telescopes like Hubble that were operating from space. I maintain that this telescope counts because it is on some ground. It happens to be on the moon's ground, but it was still operated by faithful astronaut telescope operators and is similar in function to a lot of the other telescopes that are talked about in the book. One of my favorite telescope adventure stories that I heard a lot here in Seattle happened right here in Washington State at Monastash Ridge Observatory. So this is a small observatory in south central Washington State that is used by the University of Washington and used by our undergraduates and, at the time, graduate students. It's a great research site for studying things like Milky Way stars. And at the time that this particular story took place in 1980, it was being used by graduate students to sort of launch their research. The astronomer that told me this story was named Doug Geisler. He was observing at Monastash Ridge on a beautiful night, getting the first night of data for his PhD thesis. Looking at the stories in my book, it kind of seems like the PhD thesis observations are a little bit cursed, so take from that what you will. But his observations started okay. He got a beautiful night of data, and as any good astronomer did at the time, he took careful notes on what had happened that night in the telescope's night log. So you can look at the details of this night log and you can see things like, oh, how many hours did you observe? 10. How many hours did you lose to clouds or instrument problems or other issues? None. He lost no hours. The sky conditions were excellent. And he says, the clouds cleared off on cue. I had a beautiful night. It went great. I went to bed at about 5 a.m. So if you notice the date on this observing log, it's May 18th, 1980. When I tell this story in Washington, a lot of people sit up a little straighter because that date has stuck in a lot of people's minds. Doug went to bed early on the morning of May 18th. He woke up a little bit later because he thought he'd heard some sort of weird sound. He'd heard some sort of distant rumble or boom, and he went, what was that? Okay, and went back to sleep. He then woke up at noon, a typical astronomer schedule, and started to get up and get ready for the day. And he noticed that there was no bright sunlight kind of leaking into his room around the curtains. He thought, oh no, it might be cloudy. I should probably stick my head out the door and see how it's going. He opened the door into utter blackness at noon. He couldn't see more than a few feet in front of him. If he shone a flashlight beam into the air, it just got swallowed. There was this awful smell in the air. He was alone on the mountain, running this small telescope by himself. He thought he was standing in the middle of the end of the world. He ran back indoors and started frantically tuning a radio to figure out what had happened. And what he learned was that earlier that morning, Mount St. Helens had erupted. Now, if you look at the eruption of Mount St. Helens, it basically blew off a side of the mountain. And it blew off the northeastern side, sort of the eastern slope of the mountain, and then prevailing winds carried the eruption and the ash cloud for quite a ways. So you can see what happened to Doug if you look at the satellite imagery of the eruption. So you can see where the volcano is, you can see where Doug is, and you can see what happened as the eruption sort of propagated through the air. So the plume of the volcano got blown right over Monastash Ridge Observatory, right over Doug. This is what he was standing in the middle of. And he proceeded to behave just like a very good scientist and write about it in the night log. So he knew that he would not be observing the next night, and he carefully noted hours lost 6, reason volcano, sky conditions black and smelly. He then describes going out to carefully cover the telescope because volcanic ash is very corrosive and he didn't want it to do any damage to the equipment. So this observatory log has now gone down in legend at Monastash Ridge Observatory. The log is still preserved, and it is unbelievably probably the most dramatic disruption of an observing night story I've heard. There aren't a whole lot of stories involving volcanoes. There are more than one. We have some beautiful observatories in Hawaii, which is also very volcanically active, but this was one of the more extraordinary ones that I'd ever heard. This has also now lent chapter 4 of my book its title, Hours Lost 6 Reason Volcano, sort of exploring the many natural ways that trouble can befall an observatory. You also might be able to spot the title of chapter 5, The Harm from the Bullets Was Extraordinarily Small, another story that you've now heard. The last question that I asked people as I interviewed them for this book was how astronomy had changed since they began observing and since they began working in the field. And this was a question that had a very uniform answer. Pretty much everyone pointed to how the technology of our observations had changed and what that change had done to our jobs. I got the chance to interview people who had been observing for 30, 40, 50 years, and they described how they used to take astronomical data. They would actually capture the data on thin plates of glass. This glass would be treated with a special chemical emulsion on one side that would darken when it was exposed to light. So they would order these plates from a company like Kodak that specialized in photography, and they would then carefully modify the plates so that they would be sensitive to the tiny amounts of light that we get in astronomy. People would bake the plates or freeze them or douse them in distilled water. One person swore by rubbing lemon juice on the plates. They would slice the plates down to the exact size they would need to fit into a telescope's camera. And they would do all of this work, remember, in the dark, because if the plate was exposed to light, it would start to darken. They would then carry these plates out to a telescope in the middle of the night and sit by the telescope, sometimes riding high in the telescope all night, changing out plates in the camera one after another to slowly get data on these fragile pieces of glass over the course of the night. And at the end, they would head into a dark room and develop those plates before they could even get a glimpse of the data that they had. It sounds like an incredibly arduous and sort of primitive way of getting data, but we got exquisite observations as a result. This is a photographic plate of a nearby galaxy, and you can see exactly what it is. You can see the beautiful spiral arms. You can see little spots of stars or clusters of stars in the galaxy. You really get a great glimpse of what it is. A lot of astronomers telling me these stories had really fond memories of working with these plates and sort of grappling with the telescope and sitting in cold domes for entire nights, just sort of watching the sky spin by above them. But none of them want to go back to doing things this way because they've now seen the comparison between photographic plates, as amazing as they are, and the digital data that we can get from our observations. This is the same galaxy observed not with the photographic plate, but with the Subaru telescope that I was sitting at the beginning of this talk. And you can see the astonishing difference between the two images. You can see what incredible detail we can now see in this galaxy. You can pick out really individual clusters of stars. You can see the lanes of dust sort of winding through the spiral arms and how they're blocking light. You can see the bright core of that galaxy. So the digital imaging technology that we're now able to use is amazing for our science and gives us a huge amount of information in a much more efficient manner. We now can keep data on a disk instead of on a piece of glass that we try not to break. So this has largely been an amazing change for the field. What a lot of people mention, though, is that as the technology is changing, our jobs are changing and our role as astronomers and where we are during the sort of research stargazing process is changing. Another observatory that I visited during my research was an under construction observatory in Chile. This is the Vera C. Rubin Observatory. It's named after the woman who discovered dark matter. And it's going to have a very simple but really amazing task when it starts observing in the next couple of years. Its job is to image almost the entire southern sky. And it's going to do that over and over. It can image the entire southern sky in just a few nights. So it'll do that every few nights, covering the sky over and over again for 10 years. That is effectively going to give us a decade-long stop-motion movie of the night sky. It's really easy to think of the night sky as something static that never really changes, but in reality, little things are changing all the time. You see a bright spot appear from an exploding star, or you see variable stars get brighter and dimmer, or you see a little asteroid go scooting through the sky at a strange angle relative to the stars. The Rubin Observatory is going to be capable of capturing all of this. But an interesting quirk about this observatory is that it's going to do those observations on a largely preset schedule. So this means that astronomers aren't going to travel to this observatory and sit at it and say, hey, point over there and then point over there. And I'd like to look at this thing. Do we have time? It's going to be operated on this schedule by a skeleton crew of people at the mountain. That data is then going to be put online and made available to the astronomy community, and it's going to give us just a wealth of new things to study, but it's going to capture just one type of data. It's going to be an incredible new addition to our repertoire of telescopes, but it's not going to operate alone. We're still going to need telescopes that operate in a slightly more traditional way. And my favorite argument for why this is actually a research project that I worked on a few years ago. Back in early 2011, I remember hearing from an astronomer who'd suggested that I might have found some really strange new stars in a data set that I'd already taken, and I might want to explore these some more. The stars that I'd heard about were called Thorn-Zhitkov objects. So these are very bizarre stars that look outwardly like a normal cold dying star. Now, a star like our sun, or a big cold dying star like a red supergiant, a star like Betelgeuse, is fusing elements in its core. They fuse hydrogen into helium or helium into carbon, and that's the sort of fuel source that keeps the star going. A Thorn-Zhitkov object actually has a core that is made not of regular gas undergoing fusion, but of a neutron star, this tiny dead star supported by weird quantum physics. We think we know how stars like Thorn-Zhitkov objects form. We think they're born as the result of two massive stars in a binary system. So these are stars way more massive than our sun, 10, 15, 20 times as massive. And it means that they die really spectacular supernova deaths. When the first star in this binary dies, it creates this immense supernova and leaves behind a neutron star, so this tiny thing supported by quantum physics. When the second star in the binary then expands and puffs up and cools off to become a cold red star, it swallows the neutron star. That neutron star goes spiraling into the core of the star, and you're left with this strange thing called a Thorn-Zhitkov object. It's named for Kip Thorne and Anna Zhitkov, the people who first predicted these stars' existence back in 1975. These stars had been predicted for decades, but nobody had ever found them because from the outside, they look like normal cold stars. To know that there's a weird neutron-dense core at the center requires really careful observations looking at the chemistry of these stars. We had been studying other cold stars that looked very much like these, and the idea came up that maybe there was a star lurking in our data set that was really a Thorn-Zhitkov object, and we just hadn't looked closely enough. In order to do these observations, we didn't go to a big survey telescope. We didn't just need to look at how the brightness of the star was changing. We actually had to explore its chemistry in great detail. We wound up asking for time at Las Campanas Observatory in Chile on one of these 6.5 meter telescopes there. We flew down to Chile. We spent a couple of nights there working through a star list, tweaking that star list, adding new stars at the last minute, throwing in, just one more, why not? And maybe this one is going to be the one that is actually a Thorn-Zhitkov object, and exploring what our options were in the night sky for trying to find one of these stars. Incredibly enough, we were able to look at the data as it came in and get our first hints of what we might be seeing. And the data that we get from telescopes is another one of those things that sometimes surprises or disappoints people. I tell people that I'm an astronomer and I tell people that I study stars. And I think a lot of folks imagine that I go to a telescope, maybe I don't look at it with an eyepiece anymore, but I download data and it comes out looking like this. It looks like the beautiful Hubble images that we see published. And they're really disappointed when they say, can you show me a picture of your data? And I say, yeah, I can. The data looks amazing. Check this out. This is what my data looks like. Instead of taking pictures, we're gathering starlight and we're sorting it out by wavelength, and we're looking for any bright or dim patches that tell us that there are specific elements in that star that are absorbing or emitting light at really specific colors. I think this looks lovely, but it's not something that's going to, show up on the cover of Sky and Telescope. We were looking at this data as it came in, and one of our colleagues was so accustomed to looking at this type of very strange data that she was able to recognize it almost immediately as it came in. She looked at this weird image, highlighted these things, and said, I don't know what that is, but I know that I like it. What she was seeing was in these streaks of sorted out starlight, sorted by color, little bright spots coming from glowing hydrogen atoms in the star's atmosphere. Now, generally in a star's atmosphere, atoms absorb light, they don't emit light. So these weird glowing atoms were an early sign that something was strange. When we later went back and dug through the star's data in detail, it turned out that this star did have these same chemical anomalies that you would expect for a cold star with a neutron degenerate core. So we had found the first evidence of a Thorne-Jitgov object, the first sign that this strange, bizarre type of star might actually exist. But we had done this because we'd been able to combine past survey work on the brightness of stars and observations of stars taken at other wavelengths, and the observations that we were able to get by going to a telescope, sitting at it for 2 nights, and designing the observations on the fly based on where the science sent us. When people talk to me about how astronomy is changing, they talk a lot about the technology that we're starting to use and the amazing new research we're going to be able to do as a result. And I like looking at how this technology is adding to the field rather than replacing things in the field. A telescope like Rubin Observatory is going to give us a movie of the night sky that's mind-blowing. We're going to discover so many strange new things with this telescope. And when we discover them, we're going to want to be able to follow them up with telescopes like the ones on the upper left, the telescopes that I used in Chile. We might want to look at them at wavelengths that we can't get at from the ground and jump in a telescope plane to go check them out. We might want to observe them in radio wavelengths, and as long as there aren't flying squirrels around, we should be fine. So we really need this full set of different types of telescopes, the full set of astronomy experiences, and this full set of ways to study the universe in order to keep doing what we're doing. The change in the technology has been really notable, but the questions that we're all asking and the fundamental sort of excitement and curiosity that astronomers have about the universe really hasn't. So whichever telescope and whichever type of story people were telling me, that was the real constant that I wound up running into throughout my book. So on that note, I will leave up the information about the book again, just in case you'd like to learn more about it. Thank you so much again for inviting me, and I'm happy to answer any questions that you might have. Thanks very much.
Great. Thank you, Emily, for that enthusiastic and wonderfully researched glimpse at the weird and wonderful things that astronomers do, especially the quirky times of our science. I want to encourage people now to ask questions. You've been seeing the address as the lecture went on, but I'll remind you that our questions should be asked via email to our address, which is astronomy@foothill.edu, astronomy@foothill.edu. And it's now my pleasure to introduce the current astronomy professor at Foothill College, Dr. Jeff Matthews, who's going to be curating the questions we've been getting and that we're going to continue to get. And we encourage you to keep asking questions as the evening goes on. Dr. Levesque has very kindly agreed to be here and answer questions. So Dr. Matthews, I'm going to turn things over to you.
Great, thank you, Andy. And Dr. Levesque, I also would like to thank you for speaking with us this evening. So we've had a lot of questions coming in, and so I'm looking forward to seeing more from folks. Probably more questions than we'll have time to get to. I've tried to group these together a bit, similar questions. So we have several questions, people asking about different things kind of affecting the field. And so one of these questions was, how do you think low orbit satellites, for example, Starlink, are affecting the field of astronomy?
This is a great question. And it's been a very current topic in the astronomy community. So for folks who might not be familiar with them, Starlink and I know there's a couple other constellations like this, Kuiper and OneWeb, are all these in-process satellite constellations that are, in theory, meant to one day give the whole planet satellite-based internet. Starlink is the most famous one. It's a SpaceX project. And they've been launching these huge heaps of satellites into low Earth orbit that wind up showing up as very bright dots in the night sky and as very bright streaks in our observations. There has been not a whole lot of communication between the companies that are launching satellites like this and the needs of the astronomy community. We've tried to kick off conversations like this, and they have been receptive, But launching satellites like this is just dictated by the FCC rather than anybody trying to sort of protect the night sky. So we're getting more and more of these as we're still trying to learn what it's going to do to astronomy. Our early signs are that it's really not going to be good for astronomy. You can go online and find pictures of astronomical observations that have been what we call star-linked. We'll be in the midst of an observation and suddenly you get this sort of rake of bright lines through an image. And for something like Rubin Observatory, taking so many deep photographs of the sky over and over again, this is going to be a huge problem because every satellite streak represents data that's lost forever. If there's a supernova hidden by that streak or a variable star or an asteroid, we just miss it. We can't somehow delete it computationally and get back the sky blocked behind it. These also aren't just problems when we talk about the light that they reflect. They're going to emit radio light. So radio astronomers are going to similarly be grappling with these. I think that the idea of satellite-based internet is an exciting one, but it is not necessarily the one or only or best way of trying to improve the planet's internet. And the worry about what these will do to our observations has not abated in the community. There are people, including colleagues of mine at the University of Washington, who are really focusing on how to accommodate or communicate with the people launching these satellites so that we can hopefully still have low Earth orbit satellites that meet our needs, but that don't disrupt astronomy and cause such problems for the data we're trying to take.
Got it. Wow. So, and then another question about things influencing the field and how astronomers do their work. Gary emailed in with a question asking, how has theory, physics, and cosmology's advance changed how astronomers work? So has there been any driving, not technological, but from the theory side?
Oh, the developments in astronomical theory have been mind-bending. They've been really exciting for the field because the theories that will get developed about how a star dies or what two colliding black holes look like wind up driving the kinds of observations that we take. I actually work a lot as an observer, but I also work on stellar theory and the physics of these stars, and I work with colleagues who specialize in this. And there's this beautiful feedback loop between what we think a star is doing, the physics that might be able to explain that theory, how we test that theory, and sort of this loop of how research is actually conducted. I think the best example of this is probably LIGO, because the idea of gravitational waves were purely theoretical for a little bit over 100 years. They were originally predicted as part of Einstein's work on general relativity. And for decades, astronomers swore that these should be real and invested time and energy in building these astonishing observatories. And a lot of this work was going on, not knowing if we would ever detect these. I know that there were skeptics in the community going, boy, we're putting a lot of money into LIGO. Do we think anything will ever come of it? And wow, it was an amazing day for theory when gravitational waves were discovered. And none of that work would have ever been done without the underpinning theory telling us to look for them. So the advances in theory are not quite as technology underpinned as the observational work, although our computational resources have certainly helped. We can now simulate entire populations of stars, entire mini universes, but it's still been a really amazing way to drive the field forward.
All right, and one more question related to sort of changes, and this is future changes, so upcoming telescopes. I've got a question from Joseph asking, how will large telescopes like the 30-meter telescope or the ones down in Chile help astronomers, and how will it help us find life on other planets?
Oh, that's great. I'm so excited about telescopes like this. So there are several telescopes being planned that should come online and start observing in the coming decade that are much bigger than anything we have right now. Right now, our biggest telescopes on the ground in optical light, so the light we see with our eyes, are about 10 meters from end to end. And we're building telescopes that are 25, 30, 35 meters from end to end. And they're going to be able to do things like get pictures 12 times sharper than Hubble, but from the ground. So we're going to be able to see back to some of the earliest moments of our universe. We'll look at where black holes were born. There'll be another way to look at not just exoplanets, but the sort of exoplanets that could potentially host life. A lot of this comes from their light gathering power, just the fact that they'll be able to detect such incredibly dim, tiny or far away things. And a lot of this comes from their size. The bigger a telescope is, the sharper an image it can take. It's kind of like how you use a telephoto lens to take really great sports photos from the edge of the field really far away. So these enormous mirrors are going to take really sharp little images of planetary systems in around very distant star systems, or to get really good looks at how stars shed mass or how stars move around black holes. So they're going to be technologically incredible for astronomy. They're very hard to build, and a lot of the efforts to build them are still underway. But in the next, I think 5 or 10 years, we're supposed to start having what we call first light. So when we turn a telescope on for the first time, and there'll be really exciting additions to the telescopes that we have.
Oh, yeah, I think we're all looking forward to these. Now, I've got a question here from Ingrid asking, why does the title of your book imply that astronomer explorers are vanishing?
Yeah, so I've had a lot of people ask me about the title because it sounds a little bit depressing. The title is in part a reference to the way technology is changing astronomy and what that means for the sort of adventurer astronomer, because we used to be at the telescope whenever we observed. I mentioned cases where we were literally attached to it all night and like riding in the telescope. But things have changed really dramatically since then. We still observe sometimes, but we do it from a nearby warm room inside the telescope, or we use remote operating facilities. We have a telescope we use at the University of Washington that I can run from my laptop, so I can sit on my couch and run a telescope in New Mexico. Robotic telescopes are also starting to remove people from the process entirely. So it's an exciting time for science, but it does kind of mean that what we do and the stories we have are changing. So I wanted to write a book that saved the stories of observing from a time when it was deeply hands-on. I also do want the title to be a little bit of a challenge, because plenty of people do still stargaze, either for their jobs or just for the pleasure of it. And I think it's really important that we continue to recognize and use that kind of enthusiasm that gets people to stargaze, because the technology is going to improve our capabilities, but we want to keep in mind that our curiosity and the funky questions we asked and the weird theories we want to test is still what's driving how we use telescopes. So we may no longer be physically present at the telescopes, and these adventures might be a little bit different, but hopefully the stargazing curiosity is still going to be there, so we won't be the last stargazers as long as we keep that in mind.
So speaking of people being at the telescope and observing, we've got a question from Alec asking, any thoughts about Carolyn Herschel or about the Harvard Observatory computers?
Yes. So Carolyn Herschel, first of all, I should probably explain who the computers are for anyone who isn't familiar with them. So this was a group of women working at Harvard back around the turn of the 20th century who were hired specifically to work on hundreds of thousands of spectra of stars that were currently being taken as part of a huge Harvard survey. And they wound up making some of the most astonishing discoveries in astronomy. The way that we classify stars today was invented by a woman working at Harvard, Annie Jump Cannon. And other women at Harvard made discoveries like the fact that you can use bright blinking stars to measure distances to other galaxies. Without her discovery, this was a woman named Henrietta Swan Leavitt. Without her discovery, we would not know that there are other galaxies beyond our own. And the discovery that she made is what Edwin Hubble used to measure the expansion of the universe. So the Harvard computers wound up underpinning a whole lot of research that we do today. And they were hired, at least in part, because Harvard just needed a big group of people to study these spectra, and they could hire women a lot more cheaply than they could hire men. So they were able to hire a big group of women, and lucky for Harvard, they wound up getting this decision made for, at least in part, financial reasons, wound up producing some of the most incredible scientists we've had in the field. You also mentioned Carolyn Herschel. So Carolyn Herschel is known now as one of the women who sort of pioneered the discovery of comets and of a lot of other sort of, and who built some of the catalogs that we still use in astronomy today. So she recognized a lot of these comets by sort of looking at observations and recognizing their strange, fuzzy, diffuse appearance. She was working in astronomy way back before women in science were a phenomenon at all. She primarily worked with her brother, William Herschel. And the name Herschel is pretty famous in astronomy today. People will often think of William. I think they're starting to think of Carolyn Herschel even more. So these really were women doing astronomy at a time when women in astronomy weren't common. I actually write a decent amount about this in the book, about what it's like to be a woman in astronomy and the women who had been in the field before me. And an interesting thing to read about was the barriers put in these women's way. For a long time, women weren't even allowed to run telescopes. They couldn't be the main research observer at telescopes. And if this sounds like ancient history, this was true at some California observatories until the mid-1960s. And despite this, women were making all sorts of amazing discoveries. So these policies really just put extra unnecessary barriers in their place that slowed down their science. They still got to do this research. It was just, an unfortunate product of sexism at the time.
Yeah, it astounds me to think of just how much we were, cutting into progress with people. So we've got a question from Mike asking, what happened the night that you and the operator heard the clunk and thought the secondary mirror might fall? How did that story finish?
You'll have to read the book. I can assure you that Sprue telescope is still in good shape today, but the full story of what happens to that does wind up getting told at the beginning and then a little bit later on in the book.
Got it. Okay, and so then
I didn't wind up getting known as the grad student who killed Subaru.
Right. Got another question related to telescope mishaps or situations. I've got a question from Sarah asking, why don't the bullet holes show up in the pictures?
It's a really good question, because you would expect if you just took a picture with like your phone camera and there was a spot in your phone camera, that would show up as a spot in the final image. Telescopes take nice advantage of the fact that when you are looking at something with the telescope and looking at something with that mirror, you're using the whole mirror. Another interesting example is when we design a telescope and we have a primary mirror with a secondary mirror high above it. That secondary mirror looks like it's right in the way of the telescope's view. It looks like there'd be a big hole in the center of the telescope's image. But you can test this sort of idea yourself wherever you're sitting if you just look across the room at something and then hold your hand up to your face. So look past your hand at a picture on the other side of the room or a light or a window. And you'll notice that even though your hand is right in the way, you can see around it. Telescopes can see around something like a secondary mirror sitting in the middle of its field of view, and they can see around things like those little tiny bullet holes. The rest of the mirror can accommodate for what is temporarily blocking or shielding the telescope's field of view. Now, if we had little tiny holes in the photographic plate that was taking the data, or if we had little tiny pixel problems in the digital camera, those would show up as spots in the actual image because that's where we're storing the image. But the mirror that's taking the image kind of works like our eyes in that it can see around little tiny obstructions without a problem.
All righty. And so speaking of those detectors and the things that are collecting the light, there was a question related. Yeah. So we got a question from Jamie asking, how can astronomers measure how bright things are on the chemical plate? The stars all just look black.
Yes. This is a great question. So those photographic plates that I showed, where they sort of look like little color negatives, you see a white sky and then a sort of dark dots to make stars or galaxies. Astronomers actually were able to be very quantitative about how they measured this data. I remember talking to somebody who described observing a field of stars, and the brightest stars would just basically look like darker black dots or slightly bigger black dots. And he described having a little strip of paper that was tailored to the type of plate that he had, the type of light that it responded to, and how long the plate had been exposed. And that little sheet of paper would say, a star that is this big is going to have a magnitude of so-and-so. It's going to be this bright. And a star that's this big is going to be this bright. They were able to make estimates just from that. And then from examining the plates afterward, they would, look at them with eyepieces, or they would actually be able to take rudimentary photographs or other observations of the plates, they could quantify it more. But amazingly, they could really get excellent numbers out of these plates from being very careful and very mindful of the chemical response, how long the exposure was, exactly what light they were getting, and everything else.
All right. And so then we're coming up on the last few questions here. And so circling back to the McDonald Observatory mirror, got a question, somebody saying, I saw a show about telescope mirrors being made like a honeycomb, but you said that the McDonald Observatory mirror was a thick piece of glass. Were they just lucky and hit the honeycomb part?
So now we tend to, the way that we make telescope mirrors has evolved with time. Way back when we were first making mirrors this big, we were melting enormous amounts of glass and just making single huge glass mirror blanks. And the type of mirror that was at the McDonald Observatory was one of these. Nowadays, we are able to make mirrors that are lighter and a bit more nimble by using this honeycomb pattern. A lot of you might have seen footage or illustrations, and you'll see more in the coming couple months, of the James Webb Space Telescope and how its mirror is going to work. And it's this series of 18 hexagonal pieces that all sort of fit together like a puzzle to make a perfect mirror. So nowadays, a lot of mirrors will be little tiny hexagonal pieces or little tiny puzzle pieces that fit together. Back when we were building telescope mirrors like the one at the 107-inch, it was just one big hunk of glass. There's great stories about how heavy some of those mirrors wound up being and how difficult they were to transport and support behind the telescope. But as we've been able to make honeycomb patterns or mosaic mirrors together and make them lighter, it's made us capable of building bigger mirrors and also made the mirrors a little bit easier to work with.
Okay, and so now, second to last question here. In your photo of the solar eclipse in Norway, there's a bright light coming from behind the plateau in the background. Since this isn't the rising sun, what is it?
That's another great question. I keep saying they're great questions, but these are wonderful observations. If you've ever been lucky enough to see a total solar eclipse, and if you haven't, I highly recommend it. We've got one coming up in April of 2024 that's passing through the US. But in the midst of a solar eclipse, the nature of what happens to the sun's light is such that you almost have a 360-degree sunrise. So the glow that you saw sort of over the back of one of the mountains was most likely the strange sunrise appearance that you get at the horizon. So in any direction that you look during a solar eclipse, you get that sort of strange horizon appearance. It's also possible in that photo that there was, I know they were based out of a town, and it's possible that the lights were on at the time. Although one common feature of a lot of the solar eclipse chasing stories is that these teams would sort of drop into fairly remote, fairly tiny towns. And as part of their research, they would get the whole town excited about the eclipse. One of the stories that Shadia told me was about doing this research on a very small island where they wound up working with the school principal on making the necessary arrangements. And the school principal said, we all have observed, the team had brought everybody solar eclipse glasses. And she'd explained, when the eclipse is total, you can take off your glasses and safely look at the sun without them. And then once the eclipse is ending, you have to put them back on. And he said, you tell me when, and I'll ring the school bells. So the whole island can hear it and everybody can take off their eclipse glasses to observe. I imagine that in Norway, they had probably told people to turn off all of the lights and go outside and observe. So I bet the glow really is that 360-degree sunrise. But in any astrophotograph like this, it's always a little hard to pinpoint exactly where light pollution is coming from.
Alrighty, and one final question here about changes to the field. So from Anil asking, if today's astronomers don't have to visit an observatory and the telescopes operate on a schedule, do astronomers have a day job that's 8 to 5?
It's really funny when I tell people on a plane or something that I'm an astronomer, I sometimes get asked, why are you awake right now? Because they imagine that we're permanently nocturnal and we're doing all of our work at night at a telescope. even when we went to telescopes all the time, most of our job was done during the day. Most of an astronomer's job is spent processing the data that we get and analyzing the data that we get and writing research papers about it and presenting the research and writing funding requests to keep paying for the research. So our day job is astronomer. Most of our work now is done during the day. In terms of what it means as we start to go to the telescope less and less, it's going to change how data comes in. I'm still quite certain that there are going to be observations where we need to be awake at night, either physically at the telescope or maybe on our couch using our laptop, running the telescope and dictating the observations. So I doubt that'll ever go away. Just the technology supporting it might change. So we will still have these nights at telescopes that then translate into the data that we work with during the day. I have colleagues that observe 40, 50 nights a year at telescope. I have colleagues that have observed maybe 2 or 3 nights a year. It depends on the type of observations we're taking and the type of data that we use. But our night job is astronomer and our day job is astronomer.
All right. Well, thank you so much, Dr. Levesque, for not only taking us behind the scenes in astronomy, but sharing your enthusiasm and delight at the fact that we get to do this as a job. It's a wonderful way to start our series for the 2021 and 22 school year. And we wish you the best of luck with your book, The Last Stargazer. Our next program, for those of you who are regulars, is going to be the evening of November 17th, when we have Dr. Jim Bell of the Arizona State University, who's also the president of the Planetary Society and an expert on Mars. And he's going to tell us all about the latest postcards from Mars, the amazing images and information that's coming back from our rovers, our helicopters, and our orbiting spacecraft around the red planet. So be sure to be with us at 7 p.m. Pacific time on November 17th. Until then, good night from the Silicon Valley Astronomy Lectures.